So to look at the principle of how nuclear scanning is done, you're all familiar with getting an X-ray image or a chest X-ray where you stand in front of a screen, a detector. The X-rays are generated at a source, like an X-ray flashlight, and you shine the X-rays through the patient and you detect a shadow on the detector. And that's called transmission imaging. And the image itself is bright where the X-rays are absorbed the most, and it's darker where X-rays get through and hit the film and cause a darkening of the film. And that's in the old film screen system days. You get a dark signal where you get more photons. SPECT and PET are called emission imaging, and it turns out MR is also an emission imaging technique. And that is the patient themselves becomes the source of the radiation that you're detecting. You don't transmit the radiation through the patient. You actually inject the radiation into the patient in a liquid substance in their bloodstream. The radiation goes to different parts of their body, and they emit that radiation. And so effectively, if you have the right glasses on, they are glowing when you inject this substance into them, right? It turns out they would have to be gamma ray spectacles, right? They would have to detect gamma rays, and that person would be, if they're the one that got injected, the only one in the room that's glowing with gamma rays. The advantage is that that agent goes to different organs in the body, and you can detect whether or not there has been perfusion. Sorry about that. I'm glad that finished, though. You can detect the perfusion of an organ by the fact that that agent got there at all. If that organ isn't being perfused, you won't see a lot of radiation emitted from the organ. And that's what we're going to look at in terms of cardiology or nuclear cardiology, is the heart muscle itself emitting this radiation. This is the basic structure of the scanning system itself. The patient, recall, is the source of this radiation, and so the patient is glowing and shooting gamma rays out in all directions, right? They're going in every direction. And so you would like a detector to cover as much area as possible around the patient so that you collect all of these photons or these gamma rays. You don't want them to shoot off into space and not be undetected, because that's just a waste of the energy. So the geometry of the system is to make detectors try and surround the patient as maximally as possible and still make it a practical system. So here you see two detectors approximately 90 degrees apart, and this entire structure is on a gantry which will rotate those two detectors around the patient, right? And so radiation comes out, gets detected here, and you sit in that location for some time. You rotate the detectors and sit there for some time and just collect radiation as it's coming out of the patient. And this process takes, minutes, a few minutes to tens of minutes to collect all of this radiation. Sometimes, and this slide is labeled SPECT stress imaging, because the most effective way to detect whether or not you have cardiac disease is to look at your heart when it's at rest and compare that perfusion or the signal intensity to when you have stressed the patient, i.e. put them on a bicycle, cranked up their heart rate so that the perfusion of the heart has gone up, and to see whether or not the radiation or the signal commensurately goes up with that stress. I don't know if we mentioned it before, but when you get your heart rate up to, say, 140, 150, something like that, and you're running, the perfusion of your cardiac muscle goes up by a factor of 5 from baseline, right? So there's a high dynamic range of the amount of perfusion that goes into the heart, okay? And that's required to go over the exercise dynamic range. This slide shows sort of all of the views collected by nuclear cardiology inspect all in one slide. So let's look at the top left first. Look up here at this set of images. The way this is organized is from the apex of the heart up towards the base in multiple slices. So those donuts of increasing diameter are chunks of the heart from the apex up towards the base in a short axis view. And the reason you have two sets of images here in that view is because you've done rest and stress. And you compare the rest and stress views side by side to see if the heart is underperfused in either one of those conditions. So we've gone from the base. It looks like we're going all the way up to the valve plane up here. So it takes 2 rows to get through all of the short axis views. And then here we see the long axis views of the heart. The SPECT image itself is a 3-dimensional imaging method, and so these views are sampled from that 3-dimensional volume and stuck up on the screen. Okay. So this is raw intensity after image reconstruction, shown as brightness or pixel brightness. You can color the intensity as well to make just for human perception, just to say that if you get to a certain color transition, your perfusion's at a specific level. And so you can see here there's a few polar maps, or I'm sorry, a few short axis slices here where it seems like for a large chunk, many degrees along here, the perfusion seems to be lower than the other side of the heart. So you have the other side of the heart to compare to. And in the long axis views, you can see down here, there's a chunk of tissue that seems to be missing signal. And so that would indicate that there's lower perfusion. If you want to look at the entire heart in one object or as one object, there's a couple of ways to do it. One is to reconstruct a 3-dimensional model of the heart, such as these down here. And then on the surface of that model, you can paint the intensity of the image. And so you will see a perfusion deficit would be a lower signal, a darker signal here painted on that surface. Now to look at the whole heart, you need to be at a computer and then rotate that surface around, or have somebody prepare for you, say, a QuickTime movie of that surface being rotated, and then you could just play that back, go back and forth on your phone or whatever, and take a look and see if there's a perfusion deficit. A common way of looking at the entire thing on a flat surface, so now I don't have to schlep a 3D model around, I just want the whole thing on a flat 2-dimensional piece of paper that I can print out, is to make a polar map. And this is the entire surface of, say, the epicardium mapped down onto a 2D surface. So it's like making a world map, right? So the globe is the sphere. But this is just the bottom half. So if you cut the Earth at the equator and said we're going to map the northern hemisphere onto a flat piece of paper, we project it down like this, where the apex is at the middle. And then as we move toward the edges of this map, we're moving up towards the base of the heart. And if I move in this direction, I'm looking at the septum. If I move in this direction, I'm looking at the anterior wall. This is the lateral wall out towards my left side, and then this is the posterior wall at 6 o'clock. So now you have the whole thing spread out in front of you as a 2D polar map. Sometimes this is called a bullseye plot for obvious reasons. It's shaped, like a bullseye. And the orientation is the classic cardiology orientation, where you're looking at the patient's heart from the apex towards the base, i.e. from the patient's feet towards their head, right? So that the septum, or the right side of the heart, is over here on the left side of this map, okay? Because we're looking from the feet to the head. Okay? And so this is a very convenient map because instantly you see the whole heart and you see if there's a dark spot, right? So you can make a call pretty quickly if this map is done accurately. And so it looks like for this heart, as we saw in the long axis views and in the short axis views, here's the posterior wall here. The posterior wall looks like it has no brightness there, no orange and white brightness, right? So there's a low perfusion down here. Oftentimes there is a CT that accompanies this data, and the reason is to compensate for the estimating what the attenuation of the gamma rays as they exit the patient in different directions. To do that, a CT is very useful. And then what you can do is you can take the CT, now you have a really good anatomical map, and you can map this brightness or perfusion information back into the CT space. So you have high definition, high anatomical definition from the CT, and you have perfusion information from the SPECT. The SPECT itself has fairly low spatial resolution, and we'll see why in a minute. So any questions about the basics of SPECT at this point? I'm sure there's a lot of questions because we haven't really talked about the whole thing. Yep.
For the 3D models that you mentioned, out of curiosity, how long does it take to render a 3D image? Is there a lot of computational power, or is that something that's pretty much instant after the image?
Right. So the question is, if you make one of these 3D models, how long does it take to render each view? And that's all done in real time now because of the gaming industry has made graphics cards such that you can render very complicated things. These are simple, right, because they're low resolution, so there aren't many numbers to generate that 3D model. So yeah, it's all real time now. Okay, so let's look at the utilization of cardiac SPECT, of these perfusion models. And this is a remarkable story of American healthcare. Okay, and this is why I put it in here. I mean, it's not the technology of imaging, but it's actually a truly remarkable growth in a technology. So the dots on this graph here, this is, well, first let's do the axes. This is the dollars and millions spent on obtaining these data in the healthcare system, and this is Medicare Part B payments, just Medicare, okay, which is pretty average healthcare spending, Medicare. Except it's obviously weighted towards old people, right? But anyway, the diamonds are cardiology, the squares are radiology, and these triangles are other physicians using nuclear SPECT for cardiology, cardiac SPECT. So you can see back in 1988, right? Oh, 98, I'm sorry. Got to put my glasses on for a second here. Yeah, it's 98. Not that long ago. Well, for you guys, it might seem a long time ago. So there's about $250 million a year spent on cardiac SPECT. Okay, over the next 10 years, it gets up close to $1 billion. Right, is spent on this test. Right, and it's not because the test got more expensive. It's because more and more people had this test. Right, it was basically found to indicate that it was, or thought to have, high sensitivity and specificity for detecting whether or not you had critical stenosis in a vessel causing perfusion deficits. Okay? So everybody defended it. And the rate at which people were prescribed this test, right, that's what I'm saying is the testing getting more expensive, just the rate of people getting the test went really high, right? And now you can see most of that increase, like orders of magnitude of that increase, all happened inside cardiology departments. Right? So there wasn't nuclear medicine when it's done in cancer, it's usually done by radiology. Right? So an oncologist says, I need a nuclear medicine test, they send the patient to radiology. For this test, cardiologists have this unit in their office, right? So basically there is absolutely no sort of feedback control to limit how you should use this test. Basically, what you do, you've got it in the back room, so it's super convenient for the patient and for you as a physician. You don't have to send this patient anywhere. You just say, go, we'll do a test, right? And you do the test, and then you have the results inside your own practice. And this is inside a private practice. The problem with that is you're also running a business as a private practice, right? Do you think it's beneficial to run a test versus not run the test? Which one's the beneficial one to the business? It's the test. The beneficial to the business is to run the damn test, right? Because you're going to get reimbursed for it. And the reimbursement for this was like $1,200 until about 2008. They started changing reimbursements. So you had this, and this happens in American medicine, you had this feedback system that was absolutely a positive feedback to do more tests. One, it seemed to be better for the patient. Two, it certainly was better for the business, right? And so when you get those two things together, you get a growth curve like this, right? And everybody was happy. Healthcare seemed to be being delivered better because people knew whether or not they had a perfusion deficit. Imaging companies were making more and more and more of these scanners, and cardiology practices were doing just great, right? So basically what happened was there was feedback that, hey, this is one of the largest causes of healthcare costs rising in people for heart disease. And the feedback was they dropped reimbursement rates. They started out at like $1,300. Cardiologists are fantastic at sort of going to Congress and getting a CMS reimbursement that's high. Radiologists are terrible at it. Had radiologists taken this to CMS, they would have got reimbursed $250. Cardiologists got $1,200, right? So basically, CMS said, no, this is crazy. We're going to reduce the reimbursement rate, and then the number of scans started to decrease, right? Because people, it was less profitable. In Europe, they just don't do this test that much, which is remarkable, right? On this side of the ocean, we're looking at $1 billion a year in the test. In Europe, they don't do it that much. These are the rates of CT, that's in the blue, just for comparison here, and stress echocardiography, right, are down here. And MR is somewhere in between those, right? So this test completely overshadows every diagnostic test in cardiovascular medicine in the States, but just in the States. And it's because it's reimbursed so well. Okay, so that's a little business thing about SPECT and why it's such a dominant imaging technique. Because between you and me and everybody who watches this video, it's not that good, right, at what it's supposed to do. It's just not that good. So here's how it works. I have an event that causes a gamma ray to exit the patient. And this gamma ray is traditionally it's around 140 keV, so that's off the X-ray scale. We're now into gamma rays. It's sort of right at the top end of the X-ray scale. And that photon exits the patient and hits a detector here. We'll look at the mechanism, how this detector works. And ideally, this detector produces a projection of the radiation coming out of the patient perpendicular to this orientation. You want a projection of how much radiation you have in there. And so if I have a photon that occurs here and comes at this angle and hits the detector here, the detector would mislabel that as an event that's occurring down here, right? So you don't want that. You put in these septa to basically stop photons that are coming at angles, and this detector only looks straight down, ideally, right? So when you're looking straight down and you have these septa that are limiting your field of view to straight down, obviously the deeper you go, right, the farther away you go, the larger the object is that can hit or get inside this gap between the septa, right? So as I go farther and farther down, I get a bigger field of view that can get photons into that location, right? Until finally, like when I'm 1,000 light years this way, a galaxy can get a photon into there. A galaxy's a big object, right? But that's how it goes. Right? So how does the detector work? This is technology that's been around a long time. I did experiments as an undergrad in physics on, looking at radiation coming out of various things, and we used these these sodium iodide detectors to create light flashes, and then we had photomultiplier tubes on the back of that detector, right, to detect signal when we got a light flash. And this thing, it's called a PMT, or a photomultiplier tube. It's really cool, non-digital technology, right? So you have these things here called dinodes, and there's a large voltage between this position, this dynode here, and the one at the back of the detector. As we climb along here, it's 600 volts. The whole thing can probably go to 1,000 volts. And between each one of these dinodes, you kind of focus. What happens is a light photon comes in here, creates an electron that gets ejected from this surface and hits this dynode, because there's a big voltage between the surface and the dynode. So all the electrodes come up and hit it, right? And then when they hit it, they create a shower of a couple more electrons actually off of this dynode. And if there's a voltage between this and this surface, then that shower hits this one. And then each one of those that hit create the same shower of electrons, which then hit the next one, the next one, the next one. And you can see you go up exponentially in terms of the number of electrons now that you have created by this PMT, this device. So finally, I can detect a signal that tells me that a single photon hit here, because I have enough electrons to create a continuous wave voltage that makes a signal. So this has been implemented, I don't know, since I'm gonna guess it was the 40s or something. They probably made the first one of these. I don't know. I'll look it up. But it's been around a long time. And the other thing you can do with this is, if you have a large pulse out of your PMT versus a small pulse, it is proportional to the energy of the photon that hit the original detector, right? So if you say, you know what, I'm only going to emit pulses of a certain amplitude out of my PMT to call that a positive hit, then that's equivalent to saying I'm going to take photons of a specific energy, right? And so if we have 140 keV as our energy here for the photon that comes out of the contrast agent we've injected, and we'll put a plus or minus delta E around it and emit those pulses, right? Those delta E pulses, that eliminates background radiation from other things, right? So it's energy selective. And so you change this continuous voltage pulse into essentially a discrete signal, which you can say that digital now, of when you have actually seen a positive event from your scanner. So what is done with those pulses is, we'll take a step back, where we've got these pulses coming in here, okay? And this unit, this ADC unit, basically will make a pulse height analysis to say, okay, how many, what is my threshold here, and from where did this, we haven't actually talked about where, but you're going to have a few different detectors sitting on top of your, there's a bunch of PMTs sitting. Do I have a diagram of this somewhere? Yeah, here we go. So basically, here's my detector. So these are the septa that eliminate the photons coming at different angles. So only photons coming straight up hit my sodium iodide crystal to make light, and then the light hits the photomultiplier tube, and then I get a signal out of this, right? And if I have an array of these photomultiplier tubes, when I get an event, a light event down here, and this photomultiplier tube goes off, I can localize where that occurred, right? That event. Let's go back to our. So that's what's happening here. We have a pulse come in. It says this is from photomultiplier number 6, and so it puts a click in here that an event occurred in number 6. And then the next event occurs, comes in. This is from number 2, so you put a click in here that you've got number 2, and your image is just sort of building up over time, right? So it's just a counter as a function of position. And then this is the, I forget what the nuclear transition is to go, for technetium, it creates these 140 keV X-rays or photons, and I've forgotten the nuclear transition that actually occurs. I'll look that up for you. But the primary energy, this primary energy that's coming down is centered at 140 keV. There's other stuff occurs in the, from the same molecule, but you can filter these out by this energy filter or discretization. So if you get an event, but it's at a low energy, you don't look at it. So here's our configuration. We're basically making 2 projections simultaneously in this configuration, one in this orientation, one in this orientation. You could have detectors down here at the same time, right, if you wanted to increase your efficiency by a factor of 2. And again, photon comes in here, causes a flash inside the sodium iodide crystal. The light photons hit the PMTs, and then they cause that signal from the cascade of those electrons. It's magnified, it's amplified, and it's sent to your analysis circuitry. So here are the pulses from the individual PMTs. So the photomultiplier 1, 2, 3, 4, you know where they sit on the array. So that's equivalent to positional information. And you sum up the energy from those different PMTs and use your energy bandwidth to decide whether or not to trigger that as an event, right? Is it enough energy to be an event? And then you can use the ratio of the signals from the different PMTs to decide exactly where, not exactly, but where the event occurred. So if I see 4 PMTs go off and they're all absolutely equal, then you know essentially the event probably occurred in between them all, right? So you do a spatial averaging and say, okay, I'm going to put that event right between y'all. If 2 PMTs are the ones that go off and they're equal heights, then the event would have occurred right between them. If 2 PMTs go off and one is like 50% higher than the other, then you know the position of that light flash was probably closer to that one than the other. And so you just use that ratio of those heights to determine where inside the sodium iodide crystal that event occurred. Okay, question?
How far apart are the photomultipliers?
That's a great question. So are the photomultipliers like 6 inches in diameter? No, they're about an inch in diameter. So you've got a whole array of them, usually on top of a 2D array. So there's like a 2-dimensional array of photomultiplier tubes sitting on top. And in the modern day scanner, I think they're about an inch in diameter, something like that. And so now and this is cool circuitry that actually worked in the whole era of, continuous, electronic circuits versus digital. But now we put in this signal to trigger whether or not it's an event inside our energy. These signals give you relative position, and then you just start adding them up on a digital computer to make a picture. So here's an event or a couple of events to show you how things can go right and how they can go wrong. So here we have an event. It ejects 140 keV photon. It hits the detector at a certain position. The PMTs are, this one and this one will go off, and we'll estimate where its position is. Everything's fine. This photon comes out of the patient at this direction and hits this septum and gets absorbed by the septum, and so we don't see an event. So that's good. We've not created an event where it would be assumed that it came from directly below the detector. As you can imagine, as these septa get closer together, this is an anti-scatter grid, or it's called, and as they get closer together and longer, your sensitivity to stuff that's straight below the detector is better, i.e. that geometry is better. However, you start losing more and more photons, right? The efficiency goes down as you add more of these things. Also, what can happen in SPECT, because the photons are high energy, there is a probability that some of them go through the septum, or the septa, right? This is not the septum of the heart. This is the septa of the anti-scatter grid, right? So there is a finite probability that it will just go straight on through and then land in the sodium iodide crystal. So that's a problem. And then there's another interesting problem, which is if the photon interacts with an atom inside the patient, which causes a scattering of the photon, so it leaves some energy behind and scatters off this point towards the detector and causes an event here, then you've incorrectly encoded that thing to down, a line down here versus over here. What happens when you get this scatter is not the energy going up, but the energy can decrease, right? As the photon goes this way, it deposits some energy in a collision. The energy of the photon from that collision is going to be lower than the energy of the primary photon that had this interaction. And therefore, oftentimes, when the detection of the event occurs, you can eliminate this one because the energy is lower. Okay? So if you take this septum off, if you take this thing off and you just look at all of your events, you will see a primary photo peak and then a big tail towards lower energy that is basically the scatter peak. So it looks like this. When I was an undergrad in physics, we actually plotted this thing out. So this is energy here, and this is number of photons detected. So you just have a little crystal. So we had a sample like this. It had some nuclear thing in there, and then we had a sodium iodide crystal here and a here, and it, events would happen and cause a flash, and then we had a PMT here. So no filtering of anything, right? It's just hitting this thing, and the signal you get is that you get a photo peak and then a big sort of set of stuff down here that is from these basically interactions, right? Scattering events. What we're interested in is, this signal here, which are photons that are coming just out of the patient and hitting the detector. Okay. You can also have two events occurring where, you get PMTs having voltage come out of them and off to your detector circuitry, and these add up to give you what looks like, a high enough amplitude signal, but it's just that you could have two low energy photons hit in coincidence, creating what looks like a larger photon. Why on earth you can't just do spatial, determination there? I think in the modern day SPECT scanner, this is probably not a problem, this coincident thing, because you just localize these and get their individual energies. But okay, so let's look at the depth resolution for the collimator. And so remember, in imaging, the fundamental things we're after are signal-to-noise ratio. We want a lot of signal versus the background noise. We want spatial resolution. Where did the signal come from? We would like to determine where it came from to within, for the heart, a few millimeters, right? Because the heart wall is only 10 millimeters thick. So we want to know within, a couple of millimeters where that signal came from. And we would like to be able to do it relatively quickly, not over 4 hours, but maybe over 4 seconds and maybe over, 4 milliseconds, right? Even better. So this, in terms of getting rid of these photons that are not coming from a straight down view to make our projection, right? We get rid of a lot of photons that way. The efficiency of the system goes down quite a bit, but it improves your spatial resolution. As the source moves away, as depicted in this sort of geometrical drawing, you can see that you're going to get a wider projection of a dot as that dot moves farther and farther back from your detector, right? So this anti-scatter grid works best when it's right up against the sample, and it loses resolution when the sample is at depth. The heart, if we look at, here we go. Here's our anti-scatter grid, would be right about here. The object that we're trying to image is usually sometimes 10 to 20 centimeters inside the chest of the patient, depending if they have, a 5 millimeter thickness of fat here, and then ribs, and then you go down to the heart, you can be, 10 to 20 centimeters deep. And so that's not great for spatial resolution. And this shows the change in spatial resolution as a function of depth for classic anti-scatter grids. And forget about, you don't really need to know these terms here. They're just different types of anti-scatter grid. The issue is, as you move deeper into the sample, your blur gets worse. And so they label this in the book as system resolution as measured by full width at half max. And so if I had a dot that emitted radiation, what does that dot look like on my final image? It looks like a Gaussian blur, and then the width of that Gaussian blur is this full width at half max in millimeters. So if I'm at 10 centimeters inside the object, I'm somewhere around a 7 millimeter Gaussian. Right, it's blurred out to that much, and then if I'm really deep, it can get up, a lot blurrier. And so there's as we discussed before, there's a trade-off between putting the anti-scatter grid septa closer together, which would give us a higher spatial resolution at depth, but then you lose photons, and so the efficiency of the system is reduced. Down here, but I wouldn't worry about this so much, but this is an effect that causes, this is the reason why nuclear medicine is a blurry imaging modality. So here's another configuration. I'm sure we have two projections. Basically, they're measuring the same data for the same projection, just collecting twice as many photons, right? So we look at this projection through the patient from two directions and try and collect as many photons as possible. This system then rotates around the patient as we're doing the study. Right? So mathematically, how do we put all this together? you quantify the intensity or the number of photons counted as a function of, we can call this R along here. So, it's basically a continuous variable because we're going to use our relative amplitudes of the photomultiplier tubes to position ourselves, and that's position is going to be a continuous number. And the other parameter is theta, which is the orientation of this detector. And we're going to click through values of theta, click, 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 as we take our pictures. And that will give us a set of images or raw data that are a function of R and theta. So it's a two-dimensional data set. Okay. So here, this is what raw data looks like. Right, so each one of these angles that we're showing here is assumed to be a direct projection through the patient at that angle theta. Okay, and so you can see there's the heart there. This is probably kidneys down here, and this is probably liver right here, right? So you can see where this contrast agent is taken up. It's taken up by all tissues. There's nothing here that's really completely black and not giving us a signal. That contrast agent went through the whole patient. But it did seem to accumulate in the myocardium, right? So we have more signal in the myocardium than other places. And you can kind of see the spatial resolution we're talking about just from this raw data, right? In fact, in the early days of nuclear medicine, you would say that if you look at this is a pure AP view of that patient. We're looking from the patient's chest down through their back. Let's say all we could do is one view. It kind of gives you an estimate of what's going on here. The problem is you can't really see where in the heart, if there is a deficit, it would be very hard to detect here because it's a projection, and so you don't really know if maybe the posterior wall is low. You just can't see it because it's covered up by something else, right? So that's why you do the 3D. If all you're doing is detecting whether or not this contrast agent gets accumulated, say in an organ or a metastatic tumor, right? Oftentimes in cancer, you don't really give a damn just how closely you can measure whether or not you know where that metastatic tumor is. You care about, does it exist or not? And so in cancer, if you do a picture like this, and the whole field of view just looks like this, like a normal thing, usually they use a different agent, but it's pretty uniform, then you're good. If, on the other hand, you just see dots, like bright dots in the field of view, where these METs have accumulated this agent, you're not good. And you don't, at that point, many times really give a damn if you can image the spatial resolution very well. It's just a binary decision. Is it there or is it not? Right? That's not our application. Our application is, in this organ, as a function of position in that organ, what is the brightness? And so we do care about spatial resolution. We do want to be able to detect whether or not there's brightness in the septum versus the anterior wall versus the posterior wall, etc. So that's why you go through the trouble of looking at it from different angles, like this, and then putting together a three-dimensional picture that gives you the relative brightness as a function of position in the heart. It's a lot of trouble to go through. You need a lot more data, right? Because you need many projections around the patient, and you have to decide, how do I balance my signal to noise with the precision of the image that I'm going to reconstruct? So the raw data looks something like this. This is a cartoon of raw data. And so this is position along our detector. And here are anti-scatter grid. The object is here, and we say we have, say, moderately intense radiation coming from this beige stuff. Here we'll say we have a hole in the object, so no radiation is coming from this ellipse here. And here we have, let's call it the heart, high radiation amounts, high intensity is coming from here. So when we do a projection through that object and just count up the number of photons that we assume that we have seen from, say, something, if I get a lot of hits right here, and I look down through, it's somewhere along this line, right? That stuff's coming from. You don't know where, but you just know that along this line, there's a lot of counts, right? And so that shows up in your raw data as a high number of counts, right? And if we look, there's a hole here, so the only counts that we're going to get right here along this line are from this stuff and this stuff, which isn't much at all, right? So when we plot the number of counts, we see that there's a dip here, right? And that dip is the projection of this ellipse, like onto a line, you know, for this angle, right? And so this is our projection profile, it's called. And we're going to get a whole bunch of these at different angles and put together a three-dimensional picture of the object based on those projections. And this is what we do with CT scanning as well, just the projections are made by transmitting X-rays through the patient and looking at the shadow. Here, the patient is the source of the radiation and these things are being emitted. Okay. Looking ahead to what the way CT, you know, mathematically is modeled, I think we'll go into the same coordinate system. The angle of the projection, so here's our patient, right? And we define an angle theta, which is the projection angle, right? This is the intensity profile. In nuclear medicine, this is the number of photons that are detected on our detector from the patient. In CT, it's something different. It's the number of photons that have been attenuated as we go through the line that is orthogonal to that position on our detector. All right? So basically, you ask, if I start out with 1,000 photons and 1,000 photons hit here, how many get through to here is the question in CT. And that is proportional to the integral through, like, just the amount of stuff that I march through and the attenuation coefficient of that stuff. As this number gets bigger, you get more and more absorption, right? And so it's the integration of that absorption, and then you get a number of photons get emitted and detected, and that's this number. So it's proportional to the number came in times an attenuation factor. The attenuation is proportional to the depth of the patient, like just how far it goes, and also to the amount of attenuation of the material as you're going through there. So this is the geometry of CT. We're going to look at this, and this is basically what's called the projection function. And once you have this projection function, the reconstruction of in this case, a 2D image from these 1D projections is exactly the same. CT, SPECT, PET, things like that. So as we saw with our, you know, the photographs of these systems, here's our patient or our object. The detector is in one configuration. We rotate it to a different configuration, then another. We go all the way around, right? And for this object, we see this is our profile. If this is the high intensity object, it would be right in the middle of our projection at this angle. At this angle, it's going to be all the way over on this side at small L values here, right? And so you just see all of these projections, and we're going to feed them into what's called a back projection algorithm to reconstruct the image of our slice. Any questions about that? This is a really fundamental principle thing. This back projection idea is done throughout cardiology and radiology. Okay, no questions about it? All right, I'll ask you some questions. So, how many projections do I need to make a picture? That's a pretty wide open question. Yeah.
Depends on what resolution you want.
Exactly. So I can make a picture with 2 projections, right? But the resolution of that picture is going to be pretty low, right? Because in one projection, I know I have a bright object. It's somewhere along this line, right? In my second projection, I know, let's say I make my projection at 90 degrees just for the fun of it. It's somewhere along this line, right? That's basically all I know. I know it's this bright object. So when I intersect those 2 signals, I'll get a big pulse of stuff here. But it won't be the right shape and everything. But it kind of positions where it is. But it just, all you know is it's like right about there. So if I have a dot, like say I have a point source, right? How many projections do I need? Everybody get that? So I've just got a point in my scanner, right? And I want to make a picture of where's that point. How many projections do I need? I need 2, right? Because basically, in one, say this was a tiny dot. From this projection, I know it's somewhere on this line. From a 90-degree projection, I would know it's somewhere on that line. And if it's a tiny little dot source, then I know basically where it is. Right? But I have to know ahead of time it's a dot. Right? Yeah.
When you're doing these, I guess like this data fusion for multiple scans, is it going mostly off of just like encoders on the gantry that know where your gantry is? Or
yes. Yeah. Basically, there are encoders on the gantry, and you program where you want your views and how long you stop at each view. Right. So if the patient's larger, like if it's a big patient, then you might want to stop longer because more radiation will get absorbed as it's coming out. They won't be glowing as bright, right? And so you need to compensate for that. So you basically have number of photons detected divided by whatever random noise process you have, which can be from the electronics and the photon counting statistics itself. So if I inject, say, 10 cc's of a contrast agent into a patient, and we look at the picture and it's kind of noisy because they're big and a lot of the photons are getting absorbed, how would I increase my signal to noise by a factor of 2 if I injected 10 cc's into that patient? If I'm going to do it again, and I know ahead of time, what would I change to like crank up my signal by a factor of 2? I would inject 20 cc's, right? So just put more stuff in, right? What's the downside of just putting more stuff in? It's radioactive, right? So, it's going to get absorbed, and when it gets absorbed, it does some damage, right? So there's not an open ceiling for just putting more and more of this stuff in. You need to look at what the radiation dose is to the patient. You want to keep that at a reasonable level while you're making this picture. And that's pretty well what determines how much stuff you can put in. So looking at different views of where the object is, the principle of back projection, if it's a dot and I have 2 angles, I know where it is in my field of view, right? If I take 8 projections and I do exactly the same thing I would do with 2, just like project it back this way, project it back that way. There's my dot there. With 8 projections, I get a brighter dot with respect to the background, and it's at that position, right? And then if I do 256 projections, I can recover the signal of the entire background and the dot. Here you would have a pretty funny looking image because you have all these stripes out here. And this is a pretty funny looking 2D image because it looks like a, I don't know, a flag or something, right? But you certainly know where the dot is if all you give a damn about is where that dot is. So there's an interesting balance between spatial resolution and image artifact here, right? So a 2D object, if you look at, remember these diagrams here? So these are the projections themselves. So for this object, I get fewer counts over here, so I get a byte out of it. More counts here, I get a larger signal. What I can do is take these functions and stack them as a function of theta. So theta encodes each one of these. The difference is between each one of these is theta is changing. So let's take this brightness and we'll just stack it as a function of theta. We'll click through different thetas and stack that function. When you do that, here is R in this direction, going this way. And if I stack it for different theta this way, I get a two-dimensional function that looks something like this. Right? So here's my image, and this is called its two-dimensional sinogram. And that's just as a function of R along your detector and different thetas. Right? So you can imagine that the quality of the image is determined by, how of the quality of this sinogram. Right? How big are the steps between theta would give you kind of step functions sampling this thing. Right? So you can see, because this is a trivial image, it's very simple. This big old object here is this thing sweeping through, right? And this bright object here is this thing sweeping through, right? And you, just for fun, you can in MATLAB or whatever, create different objects and take a look at their sinograms. And for yourself determine, okay, what determines how this thing changes as a function of theta, right? So we do a couple of trivial examples, right? If I have something right at the center, right, what is its oscillation in terms of theta? It's not going to move on R. If it's truly at the center, and I rotate around and take different views, it's always going to be in my center of my detector. And so something that goes straight up here, that's at the center of the picture. Right? And then as we go farther out, right, it'll start farther out, and then it'll change by a greater amount as a function of theta if it's farther away from the center. If what you reconstruct is that using this algorithm, just by, and this is like trivially, just doing this directly, just taking each one of your functions as a function of R and theta and just back projecting at the appropriate angles. That's it. So it's a trivial reconstruction, right? For that dot, you get this picture. For this image, this is its true sinogram. And then if we back project each row on this data, this is the image that results. So this is a poor representation of this object, right? So something was lost by doing this simple back projection, right? And what was lost is basically this object gets blurred extensively, right? So this, which should be a nice sharp edge, turns into this really rolling off edge. the very nice sharp edge between this object and this background gets rolled off. It's quite smooth. And this also. So there's a blurring that's occurring if you do simple back projection, right? And so we have to modify the back projection algorithm in order to use this data to reconstruct an accurate representation of the object, right? And it turns out that the simple back projection is a form of integration, right? And so to do the inverse problem, I mean, basically we've integrated this signal through here, and when you back project and you push that signal all the way back, the sum of that all the way back, you have to modify the actual signal by the Jacobian of doing integration in polar coordinates, because our data is in polar coordinates now, and we're projecting it back into XY coordinates. And so if all you do is project, you're missing something, and it turns out to be the Jacobian for polar coordinates. And that's now called, for whatever reason, a Ramlock filter, because I guess they discovered that you need the Jacobian to do the back projection. But anyway. So there are different ways to do this back projection. And the most accurate way is to just apply in terms of spatial frequency. And now this is tricky because I don't think we haven't looked at the Fourier transform, right? I don't think we've looked at. How many people know the 2D Fourier transform? Hold up your hand. Know what that is? You do? Really? Yeah, you know. Okay, about half of you. How to describe this without knowing the 2D transform? Well, to get the most, or the accurate representation of the object, the data itself, the raw data, this stuff along the R direction needs to be convolved with a ramp function. It's called, or the Fourier transform of a ramp function. There is actually no good way to describe this without describing the FT, so I think we might have to, next lecture, because I haven't got it in here, go into a bit of the FT. Anyway, to do the back projection correctly, you need to convolve each one of these 1D functions in the sinogram by a convolution kernel that has a different filter structure in Fourier space. The ramp function is the Jacobian for doing this integral, and so this is the most accurate one. However, as you can see, when you do this convolution, you get images that pass very high frequency data, but it looks really noisy. For that reason, is because all this high frequency data came through. So normally what's done is the raw data itself has a cutoff or a smoothing, and you get images that look like this. That's a terrible explanation, but we'll look at it in more detail when we look at the Fourier transform. The other thing that occurs in SPECT when you're doing reconstruction is that if you don't correct for the attenuation of the object itself, you will observe fewer events in the center versus the edge of the object, because the events in the center have to pass through more object to get to the detector. So there's a higher probability they will be absorbed, the photons coming from the middle. And they do get absorbed at higher rates, right? So if I have something in the middle here, it has to get through all this object. And so what happens is you get fewer events coming out of the middle than you do out of the edge because of the attenuation. So if you don't correct for it, your image of a uniform object will look like this, right? A profile through this object shows I get many events at its edge and I get fewer events in the middle. If, on the other hand, you know what the object is, which is kind of a strange thing for an imaging problem. It's like, well, let's make an image of an object that we know what it looks like. But if we know what the object looks like in terms of, say, its CT values, then we can estimate how it's going to attenuate these gamma rays for different pathways out of the patient. So if I take a CT of this thing, and then for each position in the object, I compute the probability or the amount of attenuation I assume is going to happen, I can correct for this attenuation factor, and so for a uniform object, I get basically a uniform signal. But this is a post-imaging correction, right, that we're going to do. This is obviously a big deal for perfusion imaging, because if you have differences, of this much to this much, is it absorption or is it actual perfusion deficit? And one of the primary ways that these images are miscalled is when the geometry of the patient has some unknown absorption direction for whatever reason. So it happens a lot in women with large breasts, for example. A breast is here, the heart's here, their posterior wall is shadowed because of the position of the breast, and then they'll call it positive, and it isn't positive. So you need a picture, CT picture of a large field of view to determine how to correct for these perfusion deficits or the reduction in signal intensity due to the absorption or the attenuation of the photons by the patient themselves. And it's a big deal. It's the primary reason why people are called false positive. It's because you get dark spots that are incorrectly labeled as perfusion deficits when they're really an attenuation. I'm sorry, I don't know what this one's about, but we're running out of time anyway. So in iterative reconstruction, you basically, it's like doing a huge least squares reconstruction using the data from the projections. And so what you can do is you can assume an activity distribution to start with, and your first assumption, the one you start with can be, I'll assume it's uniform, right? And then you calculate what would my raw data look like for that distribution, right, of activity. And so that's your first estimate of the image. You then compare your estimate to the data you actually have, the raw data you have, right? And you make a correction in your estimate based on the difference between your predicted raw data and the actual raw data. And you keep doing that comparison. You just adjust the activity, right, to try and minimize the difference between your predicted raw data given your estimate of the image and the actual raw data. And you just keep making those adjustments until finally you're under some threshold and you say stop, and that's my predicted picture, right? So what goes into that is some understanding of the noise that you expect. Because if I had a perfectly cartoon drawing of what all of my activity would be with no noise, I'm still going to get a difference between my predicted raw data and the actual raw data, because the actual raw data has uncertainty and noise on it. And so that you decide when you've reached, as good as it's going to get in terms of minimizing that noise without overfitting, right? If you start to put in tiny little features such that you reduce the differences, but all you're doing is fitting noise, then the image won't really be a good representation either. So this is called iterative reconstruction. I think probably in nuclear medicine it is now the primary way of of doing reconstruction because you're dealing with noisy samples. The reason they're noisy is because you need, say, 180 views, and you need to integrate up the amount of counts per each view, and the agent itself is decreasing. The intensity of the agent decreases over time. It has a half-life, and so basically you're working down in a low signal-to-noise regime. And then again, this we showed right at the beginning. These are the data that come out of that procedure. You get brightness as a function of position. And we went through all of these actually. Here's N diastole with short axis images here. These are long axis images here. You contour it, create a 3D model, and then do that 3D display. And then in its lowest resolution form, that bullseye map breaks the heart down into those traditional regions or areas that we discussed before. You have a map of this on one of your slides where here's the bullseye with the septum on this side. The patient's right is over here, their left is over here, their back is here, and their chest is here. So this is anterior. And it can be broken down into these regions. Most of the time, you have 6 regions in this circumferential direction and 3 regions longitudinally. So base, mid, apex. There's 4 at the apex, and there's often 6 regions here and 6 regions here. In this map, they've broken it up into finer regions, so it looks like there's 8 on the outside. So this is a person at rest. They measure their myocardial blood flow based on the amount of activity they measure in the SPECT scan in mils per minute per gram or mils per minute per milliliter of heart. And then when they're stressed, it goes up, which it's supposed to, right? In fact, you can see in this region here, the flow went up to 3.4. It started down here 1.38 at rest. It went up here to 2, but that's not normal. It should go up to about 4, say, for this level of stress. And so it looks like this person has really global low blood flow. Right? So this is with so this is rest and stress, right? SPECT. And the difference between these 2 rows and these 2 rows is you have done attenuation correction before reconstructing the pictures for these 2 rows. And you can see in the rest, no correction. There seems to be a deficit in the posterior, this is posterior lateral wall here. It seems to be less so in the stress, but when you do the attenuation correction, there's the stress and there's the rest, and that's absolutely normal heart. Okay? So, according to these pictures. Again, attenuation correction versus no attenuation correction, just to show the difference in those pictures, specifically in regions like this here, where in no attenuation correction you would call a posterior wall looks dark, but in the attenuated correction it looks reasonable on the rest. As it does on the stress, it picks up quite a bit on the stress. So these examples are basically to demonstrate that SPECT without attenuation correction is not well advised. You shouldn't do it. Okay. So these are just points for you. I won't read them out, but a big deal for SPECT is reducing radiation, because it turns out a SPECT scan a rest stress SPECT scan can be upwards around 20 millisieverts of radiation. And remember that your baseline radiation that you get each year just by walking around being alive is 3 millisieverts. And so you would like, if you have, there's obviously a cost-benefit thing. 20 millisieverts is still not a lot of radiation for somebody who you really need to know whether or not you should treat their cardiovascular disease, because that's a much higher risk operation. However, it's in looking at other scanning techniques, for example, magnetic resonance doesn't have any radiation. CT now is down to 3 for angiograms and perfusion. And so a big deal for people who work in this field and are trying to make engineering improvements is how do we get the radiation down, right? And remember, the radiation is just proportional to how many photons that patient's going to absorb when you inject this agent into them, right? So can we make good pictures with an injection that is half as much as we were originally using?